All right. Thank you, Vipin, for the wonderful introduction, and thank you for coming to this talk. So I'm Anujj Karpatne. I'm an associate professor in the Department of Computer Science at Virginia Tech, and I'm a graduate from University of Minnesota from Vipin's group. So it's back to be home. My co-presenter for this talk is Aryan Deshwal from CSE, and what we are going to do today for this talk is present a brand new set of slides that we've prepared, working together with Vipin, as a continuation of our efforts on working on the report from the AI for Science workshop that we had last year, which was focused on GenAI that Vipin mentioned. Along that exercise of preparing that report, we came up and realized several key elements that we wanted to give more emphasis on. So the first key element is that this word Gen AI keeps on getting used in different contexts in different communities, right? So there is a need to demystify what is Gen AI. Right? Second goal was to understand the rich lineage of different schools of thought in AI that have led to the Gen AI revolution. So that's another goal that we had. And the third is to understand the untapped opportunities, right? Like in this large landscape of Gen AI, what are the next frontiers? These are the three goals that we are going to address today. We'll start with an introduction to what is Gen AI, right? We'll talk about the different schools of thought, the different innovations that have played a key role in enabling Gen AI, and we'll talk about the opportunities that lie ahead, especially in the context of using Gen AI for science and engineering. So let me start with just the definition, right? What is Gen AI? So a very broad definition to Gen AI is a set of models and methods that can generate new data samples given a distribution of existing data samples. These may have probabilistic approaches that we are modeling the distribution of data samples through an explicit probability distribution, or it may be implicit as well, for example, using energy-based models. An optional element of these generative models is that they can also take as inputs some control signals that can help us condition the generation of new data samples. For example, the output of a Gen AI model could be used as a conditioning for the next sequence of predictions that could be generated in autoregressive frameworks. So this is a high-level definition of what is Gen AI. And there are several tools or methods that have been developed that are part of what we can call as the modern version of generative AI. You would have heard terms like diffusion models, variation autoencoders, generative adversarial networks, GPTs, normalizing flows, and so on and so forth. Now, this is where we are today, right? But it's important to acknowledge the sources of classical methods for generative modeling. And there are several schools of thought, but let's highlight only two. We have the Bayesian frameworks that have, for a long time, explored the problem of modeling the probability distribution of a set of data samples. And we also have methods from the autoregressive side of AI, ranging from techniques in time series forecasting like ARMA models, spatial regression models, geographically weighted regression, spatially autoregressive models. They also have an element of producing new data samples based on the local context in space or time. Along with advances in both these classical schools of thought, there has been a parallel set of developments happening in an entirely different school of development, which is deep learning, right? Which, of course, all of us are aware of. Right? Now, many of these developments that have happened in deep learning have also been enabled by the other classical schools. Right? But there are several key innovations that happened in deep learning that has sort of turbocharged this entire field of GenAI. Here we highlight three such innovations: representation learning, self-supervised learning, and contrastive learning, or sorry, context-sensitive learning. These three key innovations are still providing a simplified view, right, of what has led to generative AI. Right? But each of these innovations has its own trajectory of developments that have happened, and they're all coming together to create these modern foundations of generative AI. So what we'll do today in the next few slides is go through each of these key innovations one at a time. Right? So let me start with the first key innovation that enabled GenAI, which is representation learning. Right? This idea of learning representations is at the core of deep learning itself. Right? Where given some input features, we want to learn an abstraction of features arranged in a hierarchy extracted at the intermediate or hidden layers of a neural network. Right? This is exploring a different view than traditional approaches for predictive modeling, where we would rely on handcrafted features. Right? For example, if you're building decision trees, naive Bayes, other models, right? We would rely on feature engineering. Right? How can we convert raw features into signals that are useful for the downstream task? Right? Deep learning takes a different view, right? Where these models can be viewed as automatic feature extractors, right? That given sufficient data, given sufficient diversity of data, these models can learn the right representations in using nonlinear operations in high dimensional spaces in the intermediate layers. And this entire field of deep learning has its origins from its humble roots in modeling the human brain, going back to modeling a single neuron with the perceptron model. And since then, the field of deep learning has seen several summers and winters. The first winter being the realization that perceptrons are not able to handle nonlinearly separable data. The second winter being when we understood about the highly non-convex nature of the lost landscape of multi-layer perceptron architectures. But since 2012, right, there has been a revolution in the field of deep learning, which has been enabled by several labeling efforts that have produced large-scale labeled data sets. And this has been the case for the computer vision community. For example, the 1 million ImageNet dataset that was released somewhere around 2009. Right? Similarly, in the field of, or the domain of language modeling, right? We had internet scale text corpus coming from Brown University, coming from Google Books, right? This, all of these efforts of collecting data and generating annotations or labels had really fueled the rise of deep learning. One defining moment in the field of representation learning is the AlexNet model winning the ImageNet challenge in 2012. Since then, in the last 13 or so years, there has been several developments in the field of deep learning, and many of the innovations, especially in the last decade, were focused on predictive architectures, right? For specialized for different types of input domains, right? For images, we have convolution neural networks. For sequence data, for example, in text, we have recurrent neural networks. But all of these innovations are still mostly supervised, right? So if we just stop at representation learning, we can solve classification, regression, object detection, sentiment analysis kind of problems. Right? But there is a large variety of unlabeled data sets, right, where we don't have expert annotated labels that can still be leveraged, right, for GenAI to happen. And that brings us to the second key innovation that has led to the GenAI revolution, which is how we have gone beyond looking at supervised problems to looking at more innovative ways of thinking of how to supervise these predictive models. For example, neural networks that are mostly designed for predictive problems can be turned on their head to perform reconstruction. Right? This idea of building autoencoders goes back to the 80s. Right? There are other such tasks that we can create on the fly. For example, to contrast the predictions coming from the features of an original data sample and a slightly perturbed data sample. So this takes us to the idea of Siamese networks that were developed in 90s. Right? Now, with the rise of representation learning in the 2010s, right, is when we see these ideas really taking shape. Right? And there are several defining moments that has led to this field of self-supervised learning, right, where we are going beyond the traditional confines of supervised learning to leveraging unlabeled data, still using predictive architectures. One defining moment was this word-to-vec model that was developed that could represent words or tokens in natural language in a feature space that made semantic sense, right? Where we could look at transformation vectors in high-dimensional spaces and try to interpret what these different directions in the high-dimensional space mean. Right? Looking beyond word-to-vec, all of these methods in self-supervised learning are making some assumptions of the structure that we have in the data. For example, we may assume that things are continuous, right? Things vary smoothly across the indexing variables. And there are different types of self-supervised learning methods that have been developed. Two broad categories are self-prediction based, right, where we can predict certain elements of your data sample. One example is reconstruction, where we reconstruct all the variables. Another example is next word prediction, right, where we can predict the next word that would come in a sentence. Right? Notice that all of these problems are self-supervised, where we do not require explicit labels, right? For example, of a sentiment or a class variable. Right? We are generating this supervision on the fly, right, by creating our own problems, and hence self-supervised. Similarly, for contrastive learning, there has been several developments. One key innovation is this framework of contrastive language image pre-training, or the CLIP model that has fueled a lot of progress in image and text modalities. The third key enabler of GenAI is context-sensitive learning. And again, for this innovation to happen, we can trace its origins to methods that many of you would already be familiar. For example, k-nearest neighbors, or local learning-based methods that look at the locality, the local context of every instance to make predictions. Ideas in this broader theme would also include using Mahalanobis distance, where the distances that we are using depend on the variance or the covariance of the data that you have. Right? Or the idea of multidimensional scaling, right, where you're looking at your local context to change your feature or low dimensional representations. Now, this idea of being sensitive to the context, right, in its modern avatar is explored in this idea of using attentions in transformers, right, that are looking at the same goal, right, where we want to model interactions or associations between different tokens, between different variables, so that we can be sensitive to the context during inference as well. Right? For example, if we observe a sentence, right, and if we encounter a token such as it, we can identify what that it should be associated with. Right? In some context, it could be animal, it could be, in other contexts, it could be street. This is all happening using this idea of multi-head attentions, right, that has enabled transformers. So while this idea of transformers, right, is not directly related to using k-nearest neighbors, right, but it's the same lineage of ideas. And there are several tutorials and links that we are providing in this slide, where you can take a deeper dive into these topics. All these three innovations have led to this rise of foundation models that you would keep on hearing several times. This includes large language models, LLMs, vision language models, VLMs, and new foundation models for other types of data modalities too. Here are just some examples of foundation models that have become really popular, like ChatGPT, Gemini, the Claude model, DeepSeek, and these are just some examples. There is an entire universe of LLMs, VLMs that are out there now, doing a diversity of tasks. Some are better at code completion, others are better at reasoning. What makes them different from classical deep learning methods that are non-foundation models are three key capabilities. The first key capability of foundation models is that they can leverage diversity of different forms. They can use diversity of data modalities, image and text. They can look at diversity of data distributions, diversity of quality of data coming from different sources. They can look at data coming from different scales or resolutions, and they can solve not just one task, but a diversity of tasks. So that's one of the key capabilities that comes from representation learning and self-supervised learning. Another key capability is this new approach of pre-train then fine-tune, right? That is different from creating bespoke models that are specialized only for one task. So the idea, and this has been turbocharged because of innovations in self-supervised learning, right? So we can create our own pre-text tasks, right, using reconstruction or next word prediction or contrastive learning to learn useful feature representations during the pre-training stage using a large pool of data samples, which can then be fine-tuned on downstream tasks, enabling transfer learning capabilities. The third key capability of foundation models is their ability to perform in-context learning. And this is really the case when we have models that interface with natural language, where the outputs of these models, for example, LLMs or VLMs, can be modified and controlled not just by changing the parameters, right, which is the classical approach, but also by changing the prompt. Right? So there is a lot of work on prompt engineering, right? That provides a whole new capability to what these foundation models can do. And this has been possible because of the use of attentions or the use of context-sensitive architectures. So this provides a very high-level overview, right, of three innovations that have led to GenAI and foundation models. Here is a summary of the different innovations that we talked about in representation learning, self-supervised learning, context-sensitive learning. If you look closely, you will observe that have been primarily driven by the needs of two communities, right? Computer vision and language modeling. And that's shown by the two colors that you see here. Right? And while these have found immense success in the commercial arena, right, they suffer from several limitations in mainstream applications, in commercial applications, and especially in scientific and engineering applications. Here is just a few of them. You can find a longer list in the report. One of the challenges is their lack of explainability, their inability to generalize on out-of-distribution data, their requirements on large amounts of compute and data efficiency. So these are some of the challenges that current frameworks in GenAI face, right? And that motivates us to extend our focus beyond the traditional confines of language modeling and computer vision, to look at problems in science and engineering that have a rich diversity of the types of data coming from experiments, coming from simulations, coming from observations, new forms of modalities that are not fully represented in current foundation models, like looking at spatiotemporal data, looking at graphs in material science, looking at new formulations beyond the classification, regression, and other mainstream tasks. For example, we can look at forward inverse modeling in scientific problems, reduced order modeling, generating new hypotheses. Right? All of these new formulations can help us or can inspire us to build new innovations in GenAI. And finally, we have a rich heritage of explainable concepts and theories formalized in the form of scientific knowledge, available in different forms, including equations, laws, symmetries, ontologies, mechanistic or process-based models. So with this rich diversity of problems and properties in science and engineering, what we envision is that the next big revolution in GenAI will be inspired by the needs of a much wider class of problems, and will be used to accelerate scientific discoveries and solve problems of great societal relevance. This vision of forming a two-way street between innovations in GenAI and problems in science is exemplified by this framework of knowledge-guided machine learning, or KGML, that aims to use both data and knowledge in machine learning frameworks to rethink these traditional innovations in GenAI, right, and ground them in scientific knowledge. Right? Can we use knowledge to develop better representation learning methods, better self-supervised learning methods, better architectures of attentions that are encoding our understanding of how different variables interact with each other. And you can learn more about the field of KGML using this QR code, which covers the tutorial that we presented in the last year's workshop. So that's one of the untapped opportunities, right? Focusing on science. The second untapped opportunity comes from looking at the wider GenAI landscape, right? That we talked about these three streams of ideas, innovations that have come together. But there are several other streams, right? Several other sources or headwaters of methods or ideas that have enabled all these light green colored circles that you're seeing, which are part of the modern GenAI revolution. Right? For example, we have methods that are built on latent space models that are using encoder-decoder architectures. We have methods that build on autoregressive frameworks, right? And this is still a simplified view, right? There are many other models and many other connections, right? What this figure is trying to illustrate is that this entire universe of generative AI models has different ideas, right? And we can look at all these assumptions that these models are making to develop the next frontiers of GenAI. Right? For example, one of the streams in this GenAI landscape that, although has contributed immensely to the creation of ChatGPT and other advances in foundation model are still underutilized. Right? This is the area of planning and search that leads to reinforcement learning. And that's what I will hand over to Aryan to present further.
Thanks, Anuj. Good morning, everyone. So yeah, I'm going to talk about another class of foundational ideas that has led to all these recent advances in GenAI and some near-term opportunities, a subset which we talk about in the report. So let's talk about how do we get from GPT, which is a simple model, language model, to a chatbot that everybody in the world is talking to. So GPT-3 paper, the GPT part of ChatGPT, comes around in May 2020. Academics in computer science are maybe interested, but outside computer science academia, not many people pay attention. 2022, ChatGPT comes out and everybody is talking about an AI. So what do you think happened between these 2 years? I think the answer was already given away. It was reinforcement learning. So the GPT model, the base language model, what we call, is not really good at answering back when you ask for instructions or you chat with it. It will sometimes just continue the same question or give you harmful responses. Using reinforcement learning is what we convert this base language model into a chatbot that will answer all your cake recipes. So what is reinforcement learning? So you can think of very simply reinforcement learning as learning by acting in the world or learning by experience, which is very unlike the other forms of learning that you might have heard of, like supervised learning, where we are typically also given the correct answer in the data set. Here, the learner has to figure out what is the correct answer. So a typical setup of reinforcement learning looks like this. We call our learner here an agent because it has agency. And the agent exists in some state, in some environment. And they can take some actions in that state and get some reward from the environment. And their goal is to learn a strategy to how to take an optimal sequence of action that maximizes the sum of rewards over time. So reinforcement learning is really about this optimal sequential decision making. And as you probably can see, there are lots of problems that can be formulated under this general problem setup. So what does reinforcement learning from human feedback looks like? So in this case, our language model becomes the agent and generate multiple responses for lots of questions that we care about. And then there is a human annotator in the loop which provides the reward, which means selects preferred responses from the LLM. And the goal of the LLM agent now is to figure out how can I generate more responses which are preferred by the humans. Now you can, because this is a very general setup, you can think of lots of other settings where you can easily get cheaper rewards. So if you have math problems or programming problems, we know that in simple math problems, we know the answer. So we can ask the LLM to try generating answer for math problems or write code. And we can evaluate that using unit tests, for example, and run reinforcement learning on these tasks. What do we get out of that? We get all the recent reasoning models that you might be hearing about, DeepSeek R1, OpenAI O1. But I contend that we have still not fully exploited or unlocked full joys of RL in generative AI. And I think the big question is, especially for all of us, how can scientific problems lead to development of new RL ideas? And I think there are lots of unique challenges that arise in sciences, and a lot of us have thought about these challenges that can lead to these new developments. So I'm going to list some of them, but happy to discuss later others as well. So one of them, most of us know, is that in most real-world scientific problems that we care about, getting true reward is typically really expensive. So for example, if we say, okay, I want to use my RL to guide design of new drugs or new hardware chips or new materials, getting a true reward in these settings typically means running a wet lab experiment or running an expensive computational simulation. So the need to develop RL methods that are sample efficient is really critical for scientific domains. We also know that in sciences that we typically want to study long-term effects of interventions on these complex systems, right? So in agriculture, when we are designing decision-making policies, the effect of your actions will be very delayed. So we want to study those long-term effects regulatory biology is filled with such problems, right? Most drugs fails because they are benign. We cannot figure out their impact downstream. In many safety critical domains, we also like healthcare. If you want to run a clinical trial, we are not allowed free exploration, right? In games, we can die as many times as we like, but actions can be very risky or even unethical in these domains. So again, we need to think about RL methods that can explore safely or provide safe exploration. So there are lots of these challenges that arise in scientific domains that can lead to new development in RL. And although in today's talk, we've mostly talked about lots of challenges, I also want to mention that in the report, especially for PhD students who might be looking at this and thinking, hey, I want to solve this challenge. So we do discuss some promising ideas. And one very promising one is, at least for a subset of these challenges, is to leverage ideas from Bayesian experimental design. So the key principle in Bayesian experimental design is to really think very carefully about actively acquiring actions, which means before taking an action, I will actively think what will be the information gain I will get by taking certain actions. So, and one very flagship work in this direction has been Bayesian optimization recently, which is used very widely in material science, drug discovery, protein design, and lots of other applications. And this is especially useful for settings when you, let's say, have multiple fidelities or multiple properties you care about, or you have this evaluation cascade where different rewards come later down the line. So it's pretty useful for that setting. And as was mentioned very nicely by Anujj in the earlier part, even with RL, it might seem like all of this has come around in the last 2-3 years, but there is a long history of ideas being developed in RL across different fields, from computer science, psychology, neuroscience. And really, I believe that if you want to solve RL, you have to solve 3 challenges, which is the credit assignment problem, the exploration problem, and the generalization problem. And all of these 3 challenges have been studied very widely. In fact, 2 of very famous people who worked in this area even received the Turing Award, the biggest award in computer science this year. And even in 2010s, actually, there was a lot of interest and lots of big successes of AI in board games came from using RL. All of us probably know about the famous AlphaGo, which was a game against Lee Sedol. And I think one aspect I do want to mention here is that when I talked about joys of RL, when RL systems work, they can discover very creative things. And one very interesting anecdote about the Lee Sedol game is probably we all know about AlphaGo winning, but we didn't know that around the same time what was happening in Go was that most of the human performance was plateauing. But after these AlphaGo and AlphaZero systems came and all the game players are are learning strategies from the systems, there was a big discrete jump in the human performance. So that's what I mean by joys of RL. Now towards the end, I also want to talk about some other opportunities and areas where we are already seeing some slow inroads. And I'll obviously talk about some big challenges in these domains as well. So there are many natural or human-driven processes which occur over large-scale spatial temporal scales, and there is a growing interest in developing digital twins of these scientific, environmental, and human systems, and hopefully also incorporating human feedback. I've learned a lot from my chemistry experts and other PhD students about how molecular dynamics is very important to understand function of proteins and molecules. In climate and earth sciences, we really care about weather for lots of downstream predictions other than checking whether it is raining or not. In transportation, it's a big deal. I've learned a lot from my colleagues. Again, how simulating traffic, especially for urban centers, is very important. And what these digital twins also allow us to do is to start thinking about some control policies. So if I want to try a traffic policy, let's say, maybe I can, if my digital twin is very high fidelity, maybe I can try it there and see how it works, right? But again, right now, a lot of these ideas are coming from video generative models, are inspired from video generative models. But there are lots of mechanistic understanding in these domains, which we probably can leverage to develop new ideas. Experimental design is a big component of scientific discovery, right, where we want to design a sequence of experiments for different goals we care about. Our goal could be just learning, which means learning a mapping from design space to property space as well as we can. Our goal could be optimization. I want to find my best material, best molecule, best protein I care about. But a big challenge of experimental design in scientific discovery and engineering problems has always been the need to search over combinatorial design spaces. And as we know, search over combinatorial design spaces is not really nice. But with these generative models, one nice thing we have started seeing is that they can sort of generate lots of new possible candidates, at least, of these different types of combinatorial objects, which is very nice. And also, one more important, even in the generations of generative models, the recent one, for example, diffusion models, also allow us a lot more controllability. So if you want to generate only part of the structure while fixing the rest, which is very nice. And because I'm talking about diffusion model, and we are emphasizing a lot on advances from sciences, some of you might know that the original diffusion model paper was actually written from the perspective of non-equilibrium thermodynamics. Obviously, the big advances of Dolly and others are all inspired from vision. But again, in this domain, the critical challenge of sample efficiency remains, so we still have to be very careful about how to evaluate our candidate designs. And I think this one, last but not the least, this is all around us. Natural language interfaces have become very common for lots of things, right? We have semantic search engines. Lots of people are interested in that. So my diffusion model generates a molecule. Now, can I ask a question whether this molecule has been studied by somebody else, the toxicity of this molecule in the literature? Maybe that can be answered with, especially a lot of work in retrieval augmented generation is towards this. Lot of our interaction with software APIs is going to be with natural dialogue form now, which I'm not that upset about. But this is also what is big part of when you heard of things like, you must have heard of things like agentic systems. So a big deal of agentic systems is really that language models have shown very nice capability in generating code. And you can then use code to call APIs of these software systems. But code also needs to be secure. So we have to also think about security of code. And in this direction, formal verification is very important. And at least for me, recently, it's been very nice to see. Some of you might know of a very popular mathematician, Terry Tao. He's become a YouTuber now, using GitHub Copilot to auto-formalize a lot of math problems, which is a big direction as well, where we can now analyze proofs in these proof verification systems. But again, when we are constructing these interfaces, human-centered design is going to be a very big challenge. We have to carefully think from first principles about human-centered design in all of these things. And there is a lot more in the report as well. And yeah, thanks a lot. Happy to take some questions.